Great. Okay, so I have to start, of course, with showing the requisite what planets have we detected slide. This is an official requirement for any exoplanet talk, but it's valid and useful here. So, setting the stage for this, as we all know, the exoplanet field has just exploded in the last 30 years with over 6,000 planets detected. And basically, the takeaway is that everywhere that we have sensitivity to detect planets, we do, from the hot Jupiters that were the first detections to the ubiquitous super Earths and mini Neptunes, and even now some widely separated young giant planets. But what you'll also notice is that the planets in our own solar system on this diagram are not in parts of this diagram that we have a lot of sensitivity to planet detections for at all. And I'm going to kind of use this talk to show how what we're learning right now in terms of how to detect these widely separated young giant planets, pushing this down to higher contrast and closer in to the stars, will help reveal solar systems more like our own than we can do right now. So in terms of what we're doing right now with direct imaging, here is the gallery of some, but not all at this point, directly image exoplanets. So including our first discoveries like the HR 8799 system, which is a fairly massive star, an A star with 4 giant planets, Beta Pic B, an A star with at least 2 giant planets orbiting it. So here's B, the one that's been imaged, and C is closer in and has been detected via radial velocity and also interferometry. And here are some of the other ones that have been detected. So 51 Array B is still, I think, the only clearly T-dwarf cooler planet. Well, there's cooler, but this is the only T-dwarf planet still. And a few that have even been detected kind of embedded within a planet-forming disk. So these are protoplanets, PDS-70b and C. But all of these kind of fall into the category of what I often like to refer to as baby Jupiters. They're actually kind of baby super Jupiters. They have masses above about 3 Jupiter masses. We're catching them close to their epoch of formation, so they're less than 100 million years old. That means that there are temperatures of 600 to 1400 Kelvin, and that means that they are glowing in the near infrared. Their black body peaks are in the near infrared, and that means, and so they have more favorable star-planet contrasts than, for instance, a similar planet at a solar system age. So we're quite sensitive to this sort of planet. As long as they are relatively far from their star, we can achieve the sort of contrast 10 to the 4 to 10 to the 6 contrasts to image such a planet. And what do we gain from studying these planets? Why direct imaging in general right now for these baby Jupiter planets, but in the future for other planets as well, especially the young planets that we can detect now, because we're catching them close to their epoch of formation. They are useful for directly testing planet formation theories. I showed you at least one protoplanet that's actually in the midst of formation. Because we have light directly from these planets, we can get their spectra, which is a direct probe of their atmospheres. And this is probably the one aspect I'm going to focus on most in this talk. And then while I'm presenting these kind of baby Jupiter planets primarily here, we are working on applying these techniques and imaging cooler as well as lower mass planets, and eventually pushing down to the contrast and sensitivity necessary to detect actual twins of the Earth. And if we want to do this around a G-type star like our sun, direct imaging is the technique that's going to be most favorable for this. But continuing on, let's think more about this topic. What do we learn when we can get spectra of young giant exoplanets? And I'll use the example of this system, obviously an artist's impression here. So this is VHS 1256b. It is a 10 to 20 Jupiter mass object that is a very wide separated companion from two M stars. So we have the M stars over here, about 40 AU, about 8 arc seconds on the sky. And this is the first planetary mass object, or close to planetary mass object, that was observed and had spectroscopy with JWST. This is an example of a planetary mass object that's not close enough to its star that we have to employ a wide variety of high contrast imaging techniques. It's really easy to resolve. So here is a seeing limited image from a 4-meter telescope on the ground where you can see very nicely separated. And that meant that with only 4 hours of JWST time, using both NIRSpec as well as MIRI, the JWST direct imaging ERS program, basically we were able to get this spectrum all the way from 1 micron out past 15 microns. So this is covering pretty much the entire range of luminosity, all the light, almost all the light that's put out by this planetary mass object. And all of these little wiggles in this, none of this is noise. These are all molecular absorption features. You can zoom in to different parts of this spectrum, and there's a lot of detail. There's a lot you can learn about this object as a whole from the spectra. But let's zoom out a little bit. So I mentioned that we're covering pretty much all the luminosity that this object is putting out because it's peaking in the near infrared. It has an effective temperature, maybe about 1,000 Kelvin. So we can integrate under our spectrum. We do need to stick a model on either end to cover the small amount of light not in this spectrum, and we can get a bolometric luminosity. And with this bolometric luminosity, we can very much improve our mass estimates for this object. To an extent, this is a little bit of a tricky one. So what we're doing here is we know the age of this system pretty well, and we know its luminosity extremely well from JWST. And we can compare with evolutionary models tracking how an object of a given mass is changing with luminosity over time. And what we actually find when we do this using a technique called rejection sampling is that we get bimodality. So I can tell you with some degree of confidence that this object has a mass of less than 20 Jupiter masses, but I could not tell you whether it is on the 11 to 13 side or the 14 to 18 Jupiter mass size. And that is because this is in particular is an object that's right around the deuterium mass burning limit. So on the top plot here, the rectangle is basically the range of ages and luminosities that agree with the JWST measurement. And here are various isochrones from the models we used. And what you'll see is that here, 12.6 Jupiter masses at about the age of our object. That object is brighter than a more massive 14.7 Jupiter mass object. So the two options here, this could be a slightly less massive object that's currently undergoing deuterium burning, or it could be a slightly more massive object that has stopped deuterium burning. So in this case, we end up with a bimodality, but still quite an improvement in our mass estimate. In general, every part of this spectrum is improved by JWST. So just a comparison, this was the state-of-the-art spectrum for this object pre-JWST, and this is the JWST spectrum. So again, all of these little wiggles is opacity due to molecules. So we're looking at a variety of different band heads, a variety of different atomic as well as molecular features. And by taking this as a whole, we can learn a lot about this object. So I'm going to zoom in on these sodium and potassium lines here. And if we look at those, what we can see is that compared to old field brown dwarfs with high surface gravity, so more massive, older objects, but with similar spectral types, these have much broader features for these lines compared to these much narrower lines for VHS 1256b. So this confirms the low surface gravity and puffiness of this object, that you don't have as much pressure broadening of these lines. Um, so in this case, we're talking about probably, so it's a 10 to 20 Jupiter mass object with a radius of about 1.4 Jupiter mass objects, as opposed to these brown dwarfs, which are 30 to 50 Jupiter mass objects with a radius of 1 Jupiter radius. So much lower density. We can see that from the spectrum. We can also see that we see a couple of species that we don't expect to see at the same time. So we have this methane absorption feature at 3.3 microns. And at the same time, we saw the CO fundamental band at 4.4 to 5 microns. And we don't expect to see these two molecules at the same time. We expect either CO or CH4 to dominate. The fact that we do see both suggests that we have vertical mixing and non-equilibrium chemistry that's essentially bringing CO up from deeper parts of the atmosphere to where we can see it in the photosphere. Another thing we can get from this spectrum is direct evidence for silicate clouds in this atmosphere. So this is a bit of a subtle feature. The silicate feature is this kind of plateau feature from about 9 to 11 microns. So some brown dwarfs have it, some do not. So on the right, here is a brown dwarf with a similar spectral type that has this clear silicate feature, which is caused by silicate clouds. Here's another one that doesn't, and we're comparing the VHS 1256 spectrum against that, and you can see it very much has that silicate feature. So taken together, from this spectrum, we essentially can see that this is likely a turbulent and highly dynamic atmosphere. We know that it's low density and kind of puffy from low surface gravity. We see that there's non-equilibrium chemistry that suggests vertical mixing. And there's also this prominent silicate feature that tells us that we actually have silicate clouds there. The combination of this, the mixing, especially in the silicate clouds, which may be patchy, leads to the suggestion that this should be highly variable. And in fact, it is a highly variable object, as we'll get to in just a moment. We also have some evidence for the patchiness of the clouds from initial fits to this spectrum. So this is fits to the entire spectrum, and the best fits required both non-equilibrium chemistry and 2 cloud layers, so a lower cloud layer and an upper patchy layer, in order to fit. So if we're thinking about clouds, this kind of brings up this idea of weather, which is, I guess, essentially how cloud features are changing as a function of time. So we have evidence of the clouds. How can we get evidence for weather, especially considering that this is an unresolved object? So for a resolved planet like Jupiter, you just look at it and you see the clouds and you watch the clouds evolve and they have different colors, et cetera, et cetera. But we can actually find weather on unresolved objects by letting the rotation of the objects resolve the surface for us, by bringing different parts of the top of the atmosphere into view. So this is how the variability monitoring essentially works. And well, my movie is going to play, hooray. So here we just kind of have a possible surface map, and on the bottom, this is the light curve this would generate if you were just looking at this as a point source and watching these different features revolve around as it rotates. And so we can't take the light curve and get uniquely back to the map, but by measuring light curves like that, like this, we have some way of probing that top of atmosphere structure, showing that it's patchy, showing the impacts of these clouds and non-equilibrium chemistry. All right, so the next question is there inhomogeneous structure that we can probe for brown dwarfs and directly imaged exoplanets that would cause these kinds of light curves? I won't play this again. Clearly, that's the case for a planet like Jupiter, because we can resolve it and see that inhomogeneous top of atmosphere structure. I've actually spent a while justifying why this is the case for VHS 1256b, but in general, it's something we expect, especially for LT transition brown dwarfs. So this is comparing colors in the infrared for M stars, and then L dwarfs here. The red points are L dwarfs, blue points are T dwarfs, And connecting these, this red is kind of a fully cloudy L-dwarf model atmosphere. Blue is a fully clear T-dwarf model atmosphere, and the green are patchy cloud models. So what you can see is, to explain this transition between cloudy L-type brown dwarfs and comparatively clear T-type brown dwarfs, you need to have some sort of intermediate patchy clouds. So we do expect that, and we do expect that to cause darker and lighter patches that will then rotate around. So here's the view from a model from a general circulation model of a young exoplanet, kind of brown dwarf exoplanet boundary sort of object. And this is, in this case, again, we're going from an actual map that we know because it's a simulation, and then the resulting light curve. We're going to see the most variation if we observe this equator on, so this is this 0 degree line, but even if you're looking kind of at an intermediate angle or even at the poles, 90 degree line here, you would expect variability. So I already gave you a lot of evidence for a highly dynamic atmosphere from the spectrum of VHS 1256b. So putting all this together, it's not that surprising that it's also the most variable brown dwarf or planetary mass object known, up to 38% variable in the near infrared over about a 22-hour period. So here is comparing an epoch from 2018, where over 8 hours it varied by 25%, and then further epochs in 2020, where if you take the peak of this compared to the trough of your 2018 observation, that's where that 38% variability comes from. And this object is maybe a little bit more massive than some of the directly imaged plans I showed at the beginning of this talk, but it's a very close spectral analog. So in particular, I showed the HR 8799 planets at the beginning of the talk, and VHS 1256 is a very close analog to these planets. So we expect a similar high amplitude, intrinsic amplitude of variability, although it looks like the viewing angle is probably wrong for this. Variability monitoring is a really fruitful path for trying to understand the multidimensional structure of your atmosphere. And it seems to be this sort of quasi-periodic variability as your object is rotating, bringing different parts of it in and out of view, seems to be a real hallmark for both brown dwarfs and planetary mass objects. So here are L and T brown dwarfs, both young and in the field. So the young ones are mostly more like kind of planetary mass. The field ones are a bit more massive, but what you can see is that there's quite a few variable ones and quite a few quite high amplitude variable ones as well, with more than 5% variability. So now I'm going to zoom in kind of on how we can use this variability to characterize these sorts of atmospheres in detail. Again, this is useful for both planetary mass objects and their slightly more massive cousins, the brown dwarfs. But I'm going to use the example for a specific brown dwarf, well, actually a pair of brown dwarfs. But all of this is stuff we can very much generalize for directly imaged exoplanets as well. So I'm going to talk about some of the very first variability results from JWST. And this is for WISE 1049AB, aka Lumen 16AB. These are the two closest brown dwarfs to the Earth. They're about 3 parsecs away. They are both about 30 times the mass of Jupiter, and about the same size as Jupiter because they're the higher mass and a bit higher surface gravity than the planetary mass objects. So here's actually a resolved image of the system. And we know their masses quite well because they've been followed for over a decade now since their discovery in 2013. And so we have quite a good orbit fit. So we were able to observe these with JWST to look at, both components were already known to be variable. And we looked at them first for 8 hours with MIRI, with low resolution spectroscopy from 5 to 20 microns, and immediately followed this by 7 hours of near spec prism monitoring from 1 to 5 microns. The rotation period of A is about 7 hours, and the rotation period of B is about 5 hours. So this is covering at least one rotation period for each component with each instrument. So here's the spectroscopy. Why these kind of, you can actually see some of the variability in these points. So these are overlaying about, well, 7 hours for, yeah, this is NIRCam. So this is 7 hours of observations, but these are, again, the two brightest brown dwarfs in the sky. So that means that we get a lot of high signal to noise spectra. It takes like less than 10 seconds to get a high signal to noise spectra. So this is binned to a cadence of about a minute here. And this is just looking at thousands of these, and that's why the points look a little bit elongated, because we're overplotting. So we see a lot of the same molecular features as we saw for VHS 1256b. So features of water and CO. We again see the CO fundamental, but because we're looking at much lower resolution, we don't see as much structure. We just see kind of two absorption features. We see the same methane feature here at the same time as we see the CO. So again, some evidence for non-equilibrium chemistry as well for this object. And moving to the mid-infrared with MIRI, so we see clear water features, some methane absorption is a little tricky to see, and we do also recover a silicate feature for the A component, which is an L dwarf and expected to have these silicate clouds. So again, it's just this flattening out here, and not so much for the B component. So that's the spectra, and you can, again, the spread of the points shows you the degree of variability over this observation. But I just want to emphasize the sensitivity that we get with JWST by now moving from the spectra to building light curves. So first I'm going to compare what our light curves with JWST look like, synthetic light curves compared to HST for the same object. So what I'm doing here is taking different regions of the spectra and binning them to create a light curve. So we're looking at the peak of the J band, the peak of the H band, and then also within the water feature at about 1.4 microns. And this is what the JWST observation looks like. And on the right is a very similar observation with HST. So we get much better cadence, and we also don't have the problem of losing time in between orbits. And because we have this extremely high cadence and extremely high signal to noise, we can really plot out the behavior of this light curve as a function of wavelength. So this is for NIRCam, moving from 0.8 microns at the bottom all the way up to 5 microns for both components. The A component's on the left and the B component is on the right. And what you can see is there is a lot of evolution with wavelength, especially for B. So B has always been the more variable of the two, but we have some really interesting behavior. So one bit of behavior we have, as you can see at the shorter wavelengths, it looks double peaked. And then if we what I mean by that is that we know that the period of this from years of monitoring is about 5 hours. And if you naively just took this peak and measured a period, you'd say it was 2.5 hours, which is not correct. But if we move to longer wavelengths, it actually goes back to being signal peaked. And if you measured from this peak to this peak, you would read off about the right period. So this is already telling us something about the features at these different wavelengths. So if you could make a map of this object at 1 micron and one at 5 microns, they would look completely different. And so just to emphasize this a little more, here instead of nicely vertically spacing the different light curves, here is just overplotting them. This plot you've referred to this often as the confusogram, especially for B. So you can also see there are anti-correlations, or what we would refer to as phase shifts. Different wavelengths are peaking and flux at different times and reaching troughs at different times. I'll go into what we think is going on here. But one thing we can say for both A and B looking at these, there are kind of distinct categories of light curves here. So we used a clustering algorithm to try to figure out how many distinct families of light curves we find for both A and B. So this is using k-means clustering in particular. And what we found is that there's three main types of light curves for both A and B. And they seem to be mostly sorted in wavelengths. So we have a shorter wavelength cluster that actually kind of has the highest amplitude of variability, an intermediate wavelength cluster, and then kind of the redder, longer wavelengths. And that's similar actually for MIRI. So here are what the MIRI light curves look like. Again, quite a lot of structure, quite a lot of variation as a function of wavelength. But you can see there's kind of a clear break in structure for both of these right between 8 and 9 microns. So doing k-mean clustering, same thing, where we get two different clusters for MIRI. So now if we take all the light curves as a function of wavelength and look at what clusters they've been assigned to as a function of wavelength, this is for the B component, but the A one is not dissimilar. And again, there are three main clusters in NIRSpec and two in MIRI. And our interpretation of what is going on here is that essentially each of these clusters is probing a different opacity level, a different depth in the atmosphere. The photosphere is at a different point. So we see kind of this global shift right here at 2.2 microns, another global shift at 4.2 microns, and then a third global shift at 8.5 microns. The 8.5 one is very close to this onset of silicate absorption. And the other two seem to be very close to CO features. And then occasionally we also see these kind of smaller shifts. And what's notable about these smaller shifts is that they're often within known absorption features. So I'll point out this methane feature right here. Our interpretation of the different clusters coming from different heights comes essentially from this. So the interpretation here is that what's going on is when you have opacity from methane right at this 3.3 micron region, you have a higher opacity, and that means you're seeing a bit higher up in the atmosphere at a higher level, and that pushes you to this higher level cluster compared to the adjacent wavelengths where you have less opacity and can hence see deeper down. So the interpretation is that cluster 3, deepest, cluster 2, kind of intermediate, cluster 1, moving up higher in the atmosphere. And by comparing with contribution functions from models, this also agrees with this general picture. So in general, we expect shorter wavelengths are going to primarily probe deeper, hotter, higher pressure levels. Longer wavelengths probe primarily higher altitude, lower pressure levels. It's not one-to-one, but you can see that there is a general trend comparing to this contribution function that's basically just showing us for this particular model where light is coming out. Each of these times we have kind of a global shift. So this bandhead here, you can see that past the bandhead, this is where you kind of move up to a lower pressure, higher region, and then another time here as well. So that's kind of the main takeaway from this. Again, the idea is the way we can try to explain all of this different structure as a function of wavelength is mapping it onto pressure levels via contribution functions. But what is generally clear is then if you can look at each of these pressure levels and make a map at each of these wavelengths, you would actually see a lot of different structures. Like if you look at it at 1 micron, your object is just going to look completely different than if you look at it from 5 microns. Okay, so that's kind of the digging deep into what we can do in terms of characterization of a single object. I'm going to spend the rest of my time justifying why we need to find more of these objects to characterize. So these two brown dwarfs are very similar kind of temperature range, although a bit more massive than the baby Jupiters that we can image. But I'm going to kind of just argue that the new frontier and what we need to do next is to move to cooler planets, and eventually lower mass as well. And part of that is that the cooler you go, the more cloud species and atmospheric physics you can probe. So we've been talking about L dwarfs and T dwarfs, and a tiny bit about M dwarfs as well. And essentially, the temperature of the object is going to determine what you see in the photosphere. So for our hottest objects, you have titanium oxide, corundum, and then when you move a little cooler to your L dwarfs, this is when we get those silicate clouds we were talking about. And then below that, you have actually iron metal droplet clouds, which sound really unpleasant. But then if you just move deeper down, well below the photosphere, you get down to the same titanium oxides and corundum that you get for M dwarfs. And similar then, if you move cooler to T dwarfs, you start to be able to probe all sorts of other atmospheric physics. So you get some salt clouds. You also have potassium. Well, actually here are salt clouds. Up here you get your methane as well. And then if you can move to even cooler temperatures, again, everything else is still living down below the photosphere. But you start to be able to potentially even look at water clouds if you are moving cool enough. And this is really the new frontier. We've just entered the era of looking at essentially, well, not as cold as Jupiter, but more temperate exoplanet atmospheres. So in the last 2 years, we now have 3 temperate exoplanets imaged. I'm defining temperate as less than 400 Kelvin, but these are all mostly kind of like 250 to 300 Kelvin objects. The first of these was EPS Indi AB, so this planet. So it is about 6 to 8 Jupiter mass planets. And it was detected first via radial velocity. It was the first radial velocity planet to be imaged. It is an old, cold planet in the solar neighborhood. So it's the first one that really moves out of this paradigm of, oh, we can only look at these hot, young planets. And very similar to this is 14 Her-C, also detected via radial velocity, also an old, cold exoplanet, and fairly massive. And then on the left here, this is TWA-7b. So this is cool as well, but for a completely different reason. So this is quite a young system, about 10 million years old, and it's cooler because it's a lower mass object. So this is the first Saturn mass planet imaged. So filling in where these go. So we're essentially, JWST is opening up a temperate young system discovery space, temperate old systems that have been detected via radial velocity, but also more objects like TWA-7b, which are cool because they are lower mass. So very similar in terms of separation and age to the hotter young giant planets, but just requiring better sensitivities to detect. Eventually, we're going to hopefully move further in. This is where we will eventually get with ELTs, but we're not there yet. So one theme that I haven't harped on with the widely separated young giant planets is that they do appear to be fairly rare. We've had a number of large surveys that have looked at hundreds of stars and have detected on order a handful of planets. But there are some suggestions that if we can move to lower masses, the planets may not be so rare. So this is looking at specifically at radial velocity studies that are moving outwards that suggest that there may be an enhanced popular of sub-Jupiter exoplanets. So the Jovian exoplanets are the green here, and yeah, just not a lot of them. But at least from radial velocity, there's a hint that when you can move to below Jupiter masses, that there are more planets to detect. And out here, we have no empirical constraints from radial velocity. I'm going to end by telling you about the empirical constraints we were working on from direct imaging. So we can target planets in this mass range, in this separation range, around young systems by looking at young moving groups. So younger age gives us access to lower mass companions because we have essentially degeneracy between age and brightness. If you have a very young thing, is obviously starting bright and cooling off, and an older thing, to have the same luminosity, needs to be more massive. So without knowing age, we can't tell if a given object is a young planet or an older brown dwarf at the similar luminosity. But if we can choose stars with well-defined ages because they're members of young associations, they're all moving together, we can access these lower mass companions. And then the next goal is to try to observe things as close as possible, because that gives us better physical separation. So the sweet spot are these young moving groups. They're a bit older than young star forming regions that happen to be a bit further away, hence we lose physical resolution. And these objects here are all mostly within about 60 parsecs, and ages, we tend to focus on the ones that have ages of less than 100 megayears. In the last 2 years, we've been able to survey about 170 of these using JWST. So this is from 3 different programs. The first, we're targeting 2 specific moving groups. So TWA Hydra, which is about 10 million year old association, looking at 23 stars with that. And then Beta Pic moving group is about 20 million years old and looking at 56 stars in that. And then the last is a survey program. What this means that is it was a filler program. So it was to fill gaps in the schedule. And this was targeting a number of different moving group stars within 60 parsecs, mostly looking at FGK stars. So here's just a fun visualization of all the data in a non-random, interesting choice of pattern. But the point is, with 170 stars, this is the first statistically significant sample that's been observed for sub-Jupiter planets. So we observed these with NIRCam, and that allowed us to simultaneously do coronography at both 2 microns in the F200W filter and in the F444W filter simultaneously. So here again is just our total sample here. So mostly M stars in the Beta Pic moving group in TWA Hydra, and then a range of FGK stars in a variety of other young moving groups. So this is the sky distribution of the targets that were observed for survey 6005. And here are all of the F444W images after a lot of processing. So that could be a whole talk in its own. So we're not going to talk about how we do coronography. We just have a magical black box that does our post-processing. What it's doing is we're essentially using the fact that we're at the diffraction limit with JWST, and any star is going to look the same, to build a very high fidelity PSF model and subtract that away and remove all the starlight until we can see all sorts of things in the field of view. Some of these are exoplanet companions. Most of them are not. And one thing we have been finding working from space and working at the incredible sensitivities of JWST is that we find a whole new different type of background contaminants than we did with these ground-based surveys. So in ground-based surveys, all the background contaminants were like 99% stars. We still see those. So this little snowflakey thing is what a star looks like when you do coronography with JWST. It looks nice. It has a lot of PSF structure, a whole lot of PSF structure, but it looks nice and sharp. And now with JWST, we're going so deep that we see background galaxies. We generally know they're background galaxies because they look fuzzy and extended in a way that a star should not. And so this is why we observed in these 2 filters simultaneously. Because, well, we can throw away a lot of contaminants because they look extended, but having instantaneous colors really helps us remove a lot of other contaminants. So here's an example here. I mean, you can see it's a galaxy because it's extended, but this object is brighter at F200W and fainter at F444W. If we consider the spectral energy distributions of young planets, they should always be brighter at 444W. They should probably actually completely drop out with our contrast limits at F200W. So we can immediately say this is too blue to be exoplanet companion. So over last year, we went through the process of finding all the point sources and extended sources in our field of view and putting them on color diagrams. So here, these are just the F200W versus F44W colors versus absolute F444W here. All of these are exoplanet candidate companions that have survived some vetting steps. They're arrows because they're all dropouts in F200W and only detected in F444W. GJ 504b is a true exoplanet that we observed as part of the survey in case there was additional things in the system, and we're comparing against models of exoplanets, just, of what we expect their colors to be. So these all have consistent colors for exoplanets, and we threw out many, many things that didn't. You can see the sort of things we threw away in this middle panel. So here we're comparing those colors with the apparent F444W magnitude. So again, here are our candidates that we've held on to. These points here, the yellow circles, are stars from a galaxy model. You can see they're much bluer than our exoplanets, so we can throw away stellar contaminants by their blue colors. And here are those new galaxies that we haven't had to think about from the JADE survey. And mostly they're bluer and fainter than our candidate companions, but we do have some overlap that is problematic. But if we keep our objects that have passed some of these tests and look at their predicted model mass versus separation, what you can see is that these are mostly sub-Jupiter mass, and some even sub-Saturn mass. The bottom here is some of our best candidates that we can make look the nicest. This one is actually very close to being confirmed, but we can't declare victory at this point because even if these have the right color, even if they don't look extended, we could get unlucky and they could still be a background brown dwarf or even a background star with weird colors. So what we have to do is come back in a year and try to make sure that these little points are moving with common proper motion with their star. And so I'm very happy to say that we had put in a Cycle 5 proposal for this. It was accepted, so we will be able to actually confirm all of our little planet candidates. And hopefully next time I can have an update about what we found for those. And this was the main thing we were going after with these surveys. But one interesting side effect and one interesting result we weren't expecting, we started imaging lots of circumstellar disks. Some of them haven't been imaged for the first time. I mean, haven't ever been imaged before. So here are some of them. We actually have on order about like 15 detected in the data right now. But these are the ones that are new discoveries or first time being resolved in scattered light. And one thing that's been quite interesting is a lot of them have been around M stars. And we found in particular some very large disks around M stars. So we don't have a good answer for what's going on there yet. And this is all very much in progress. Yeah, okay. So I think that's about it for this section. And I think that's probably going to be it for me as well. Yeah, no, we don't have time to go further to the future. Maybe I'll throw up one more slide on that. So I think the takeaway here is we've only imaged 3 temperate giant planets confirmed at this point, but I think that we're going to have a lot more of these in the next few years. And I think they unlock a lot of interesting atmospheric physics. But I think another key point here is one reason to study these sorts of temperate giant exoplanets is that they actually do have similar temperatures to the Earth. They're a type of planet we don't have in our own solar system. But especially the young ones, we know that these are not environments that we could have life in. So they give us a very important kind of baseline of what a non-habitable atmosphere at Earth temperatures can look like. That's going to be important moving forward in terms of the eventual goal that everyone is definitely focused on very long term, which is imaging of exo-Earth twins eventually. So I'll just kind of end by saying that the key point here is that eventually, with telescopes such as the Habitable Worlds Observatory and the Life Observatory, the goal is to not just be characterizing young giant planets of various form or much more massive giant planets in the solar neighborhood, but to push this down to planets like the ones in our own solar system, and in particular planets like our own Earth. Okay, I think I will end there and happy to take questions.
Amazing. Thank you very much, Beth. If anyone has any questions, please can you raise your hand in Zoom, and then I call on you, you can unmute and ask a question. Okay, I have one to start with. Like roughly currently, how many sort of directly imaged planets are sort of at the moment are we able to observe with JWST, and how many more do you think we'll find in the coming years?
Okay, so in terms of the known ones, I think most of the known ones are observable with JWST. I would argue so if you look at the Exoplanet Encyclopedia, they have like 60 or 70. I would argue that we have a couple dozen at most. And all of those are doable with JWST. It's just that you can only really choose the very most promising ones given the oversubscription. JWST, I think, is likely to detect tens of exoplanets. We'll see what happens. I mean, I will have a much better answer for you in about a year. And I think, the story with direct imaging in general, as we move to cooler, lower mass planets, as we move closer in, eventually we know those planets are there from radial velocity. We're going to start having hundreds of and maybe up to thousands of direct imaging detections when we can just push far enough in, which is not quite where we are yet.
Yeah.
ELTs will probably do that.
We've got a question from Victor Vincent asking, for moving groups, what's the distance limit for JWST observations based on contrast limits?
Oh, how far out can you go moving group wise? Is that the question?
Yes.
Okay. So you can go really far out. Like if you want to even go to the young star forming regions that are more like, 150 parsecs away, they're still observable, especially if you want to use NIRCam instead of MIRI. MIRI is going to be limited by your background. The problem is, and there's reasons to do that because if you're say looking at Orion and you're less than 1 million years old, your planets are going to be absolutely at their brightest. But the problem is you're going to sacrifice physical resolution. That means that, at Orion, you're going to be looking at only the very whitest planets, maybe like 100 to 500 AU from their star. So that's the trade-off there. You certainly can go to more distant clusters. It's just that you lose physical resolution.